Hello, dear professor. I am Siraj. Now I am present my presentation. So, my presentation topic: environmental and dietary exposure of perfluoro octanoic acid and perfluoro octane sulphonic acid in the non-rival Korea. Now I am coming to abstract. This study performed the first environmental and dietary exposure assessment to explore plant uptake of perfluorooctanoic acid and perfluorooctane sulphonic acid from agriculture site and irrigation water in the Nakhon region of South Korea. Plant uptake: perfluorooctanoic acid and perfluorooctane sulphonic acid from agriculture soil and irrigation water. Annual average concentration of total perfluorooctanoic acid and perfluorooctane sulphonic acid ranged from 0.026 to 0.112 microgram per kilogram irrigation water, and from 0.818 to 1.364 microgram per kilogram soil respectively. According to this data, the concentration of perfluorooctanoic acid and perfluorooctane sulphonic acid in soil are greater than water, which are 0.818 to 1.364. The concentration of perfluorooctane sulphonic acid and perfluorooctanoic acid are higher in soil from water, which is 0.026 to 0.112 microgram per kilogram. The observed average biennial concentration of the sum of perfluorooctanoic acid and perfluorooctane sulphonic acid decrease in irrigation water from 0.112 microgram per liter in 2013 to 0.026 microgram per liter in 2015. The annual biennial concentration are decreased between 2013 to 2015 from 0.112 microgram per liter to 0.026 microgram per liter. Pollutant Control Act may have helped to reduce level of PFAS at this location. According to by the Act of Organic Pollutant Control, they reduce the concentration of perfluorooctanoic acid and perfluorooctane sulphonic acid from 0.12 microgram to 0.026 microgram per liter. This study calculated some of the highest plant uptake factor reported to data with a value ranging from 0.962 in green onion to 0.04 in plums. The perfluorooctanoic acid and perfluorooctane sulphonic acid are present in different plants. The concentration are different in different plant. In plum, the concentration are 0.04. In green onion, the concentration are 0.962, which are higher from plums. Leafy vegetable and rice are important component of the Korean diet. Leafy vegetable and rice are the important component of the Korean diet, and these pollutants are present in rice and vegetable. These group had the largest contribution to the estimated dietary intake of perfluorooctanoic acid and perfluorooctane sulphonic acid, which was calculated at 0.449 and 0.140 nanogram per kilogram BW per day respectively. It is the unit of daily it is the unit of estimated daily intake which are used for the concentration. This corresponded to 66.4% for perfluorooctane sulfonic acid and 7.9% for the perfluorooctanoic octane sulfonic acid of the EFSA reference dose. The direct intake of perfluorooctanoic acid and perfluorooctane sulfonic acid from crops along diet not exceed the RFD. However, when the estimated daily intake EDI from other sources such as tap water, meat, fish, dairy, and beverage was included in the exposure risk assessment. Both the EDISM to perfluorooctanoic acid and perfluorooctane sulfonic acid. Perfluorooctane sulfonic acid and perfluorooctanoic acid are present in tap water, meat, fish along with soil and irrigation water. Introduction of perfluorooctanoic acid are the conjugate base perfluorooctanoate, IUPAC name pentadecafluorooctanoic acid. Other names are used for perfluorooctanoic acid or perfluorooctanoic acid or perfluorocuprolic acid. Chemical formula C8H15O2, molar mass 414.07 gram per mole. Appearance perfluorooctanoic acid appear in white solid, in the form of white solid. Density 1.8 gram per centimeter cube. Melting point 40 to 50 degrees centigrade. Melting point 40 to 50 degrees centigrade. This soluble in water due to a hydrogen bond, polar organic and also soluble in polar organic solvent. Perfluorooctane sulfonic acid and are the conjugate base of perfluorooctane sulfonate. The conjugate base is the chemical formula C8H17O3S. Molar mass 500.13 gram per mole. Boiling point 133 degrees centigrade. The pKa value of perfluorooctane sulfonic acid is lesser than 0. Introduction for fur and polyalkyl fluoroalkyl substance have been widely used in the fabrics, paper, metal, surfactant and electronic industry since in the 1950s. Two of the most widely used PFAS include the long chain. The fur and polyfluoroalkyl substance are widely used in fabrics, paper, metal, surfactant and electronic industry. Those industry which are made electronic substance, the fur and polyalkyl substance are used in the industries. Fluorooctane sulfonic acid and perfluorooctanoic acid, these have high detection frequency, bioaccumulated in crop, the environment and human and are highly toxic. Due to this toxic material, the environment are highly toxic. Both of these substances have classified as persistent organic pollutant by the Stockholm Convention. The major exposure pathway for human is through the injection of perfluorooctanoic acid and perfluorooctane sulfonic acid accumulated in food and water. The International Agency for Research on Cancer classified perfluorooctanoic acid and perfluorooctane sulphonic acid is possible carcinogenic to human. These are, according to the International Agency Research, these perfluorooctane sulphonic acid and perfluorooctanoic acid are carcinogenic to human. The major source of PFAS in human diet are from dairy, fish, and meat product. The toxic material, especially for fluorooctane sulphonic acid and for fluorooctanoic acid, are coming from dairy, fish, and meat product. Little is known about exposure from plant-based product. Although exposure from these sources is believed to represent a major a source due to their relatively low bioaccumulation factor. South Korea, a developed and industrialized country, previously used PFAS in the textile and electronic industries. The South Korea are the industrialized and developed country, and these chemicals are used in the industries and coming from industries to soil and water, and from soil and water the plant uptake these chemicals. Several studies have identified elevated concentration of PFAS above EFSA annual average environmental quality standard for surface water 0.65 nanogram per liter perfluorooctane sulphonic acid in the US Environmental Protection Agency health advisory value for drinking water. The source of these exceedance was stipulated to be from factors such as the potential use of biosolid from wastewater treatment plant, irrigation water, and illegal or accidental discharge. Maximum concentration of perfluorooctane sulphonic acid and perfluorooctanoic acid downstream of the neutron arrival were recorded as 0.183 microgram per liter and 1.12 microgram per kilogram for water and soil respectively. These are the concentration of perfluorooctane sulphonic acid and perfluorooctanoic acid in soil and water. 6 years after the past baseline survey, most studies have focused on correlation between potential dietary source of PFAS and impact on human health as well as dietary exposure and impact on sex and age. The major impact of perfluorooctane sulphonic acid and perfluorooctanoic acid on the human sex and age. It is the location of neutron arrival. In these from these arrival plant coming to soil, plant uptake water, and these the water of the neutron arrival contain perfluorooctanoic acid and perfluorooctane sulphonic acid, which are the organic pollutant. Result and discussion: perfluorooctanoic acid and perfluorooctane sulphonic acid resides in irrigation water in knockdown arrival. Perfluorooctanoic acid and perfluorooctane sulphonic acid were detected in water sample from all study sites. The average perfluorooctanoic acid and perfluorooctane sulphonic acid concentration in 48 irrigation water sample throughout the study period was 0.042 plus minus 0.0 0.042 microgram per liter and 0.027 plus minus 0.068 microgram per liter respectively. The concentration of perfluorooctanoic acid and perfluorooctane sulphonic acid in irrigation water sample are 0.042 plus minus 0.042 microgram per liter. The average of the sum of perfluorooctanoic acid and perfluorooctane sulphonic acid in 2013 and 2015 was highest in winter at 0.01 microgram per liter. Between 2013 and 2015, the concentration of perfluorooctane sulphonic acid and perfluorooctane octanoic acid are higher, which is 0.101 microgram per liter. In summer and 0.060 microgram per liter. In autumn, with the lowest concentration of 0.047 microgram per liter recorded in spring, 0.06 microgram per liter are the concentration in summer, and the lowest 0.070 microgram per liter are the concentration in summer, but the 0.060 microgram per liter are the concentration in autumn, and the lowest concentration are recorded in spring, which is 0.047 microgram per liter. Concentration peaked during winter from the southern side and at the beginning of the summer from the northern side in 2013. The concentration peaked during winter from the southern side and at the beginning of the summer from the northern side. In winter, the highest concentration from the southern side, and in summer, in the beginning of summer, the highest concentration from the northern side. Perfluorooctane sulphonic acid and perfluorooctanoic acid reside varied seasonally in the southern side in 2013, with the greatest perfluorooctanoic acid and perfluorooctane sulphonic acid concentration in water in winter 0.129 and 0.107 microgram per liter respectively, followed by perfluorooctane sulphonic acid concentration in autumn 0.094 microgram per liter. Perfluorooctanoic acid and perfluorooctane sulphonic acid concentration in summer 0.089 and 0.033 microgram per liter respectively, and perfluorooctanoic acid 0.029 microgram per liter and perfluorooctane sulphonic acid 0.023 microgram per liter in spring. In spring, the concentration of perfluorooctane sulphonic acid 0.023 microgram per liter. The average perfluorooctanoic acid and perfluorooctane sulphonic acid concentration in the southern side were 0.067 and 0.064 microgram per liter in 2013 respectively. This decreased to 0.019 and 0.009 microgram per liter respectively in 2015. The average perfluorooctanoic acid and perfluorooctane sulphonic acid concentration in the northern side in 2013 were 0.059 and 0.016 microgram per liter respectively. This decreased to 0.020 and 0.003 microgram per liter respectively in 2015. Industrial activity involved paint, metal, and recycling factories were located near site A to C during assembling, whereas other sites were at least 100 meters away from industrial activities. Non-rival A to C side A to C are nearest to the industrial, where the industrial activity, different industrial activity occur, paint, metal, and recycling factories. From these activities, the organic pollutant coming from industries to knock down a river. This contamination inside A could be attributed to localized disposal of pollutant into irrigation water way of the Nekton river. Additional 6 samples from the site were analyzed from June 2017. The result indicated that perfluoro octanoic acid concentration continued to decline 0.017 microgram per liter, and perfluorooctane sulphonic acid concentration remained relatively stable 0.005 microgram per liter. A high concentration of perfluorooctanoic acid and perfluorooctane sulphonic acid corresponded with elevated levels of rainfall documented in boson from 2013 to 2015. These are the different value of perfluorooctane sulphonic acid and perfluorooctanoic acid. These are the average value of perfluorooctane sulphonic acid and perfluorooctanoic acid. Conclusion and recommendation. This study explored the influence of perfluorooctanoic acid and perfluorooctane sulphonic acid contaminated water and soil on plant uptake and its impact on dietary exposure in and around one of the largest river in South Korea, the Mekong river, over a 5-year period 2013 to 2015. Plant uptake the organic pollutant, especially perfluorooctanoic acid and perfluorooctane sulphonic acid, from soil and irrigation water. The annual average concentration of the sum of the perfluorooctanoic acid and perfluorooctane sulphonic acid concentration in the irrigation water exceeded the California OHAL's advisory guideline for inland surface water. This study identified that plant uptake of perfluorooctanoic acid and perfluorooctane sulphonic acid can be a significant pathway for human exposure. Plant uptake factor greatly varied with a different crop type ranging from 0.4% plum to 96% green onion. The concentration of perfluorooctanoic acid and perfluorooctane sulphonic acid in green onion are higher, and with leafy vegetable appearing to accumulate the highest concentration of perfluorooctanoic acid and perfluorooctanoic acid and perfluorooctane sulphonic acid. And also leafy vegetable also accumulated the highest concentration of perfluorooctanoic acid and perfluorooctane sulphonic acid. Result and recommendation continue. Although the perfluorooctanoic acid and perfluorooctane sulfonic acid reside in soil did not exceed the advisory Canadian guidelines for agriculture. The perfluorooctanoic acid EDI values of the local crops almost reached the proposed RFD. When combined with estimated impact from other sources, the EDIs of the perfluorooctanoic acid and perfluorooctane sulfonic acid for people consuming vegetable grow in the study site would likely exceed both of the RFDs. It is not currently clear whether the perfluorooctane sulfonic acid and perfluorooctanoic acid recorded in these samples were predominantly due to plant uptake from soil and uh, for water or from PFAS introduced to the surface of the plant by irrigation water. It is not clear the plant uptake perfluorooctanoic acid and perfluorooctane sulfonic acid from soil or for water or from perfluoro or from PFAS introduced in the surface of the plant by irrigation water. The results of your research point toward the positive impact legalization can have in reducing environmental concentration of perfluorooctanoic acid and perfluorooctane sulfonic acid. However, not all PFAS are regulated to the same extent. Conclusion and recommendation continued. The result of our research point toward the positive impact legalization can have in reducing environmental concentration of perfluorooctanoic acid and perfluorooctane sulfonic acid. However, not all PFAS are regulated to the same extent. Therefore, the decrease in concentration in perfluorooctanoic acid and perfluorooctane sulfonic acid identified here may be offset by increased use of emerging PFAS such as carbonate replacement hexafluoropropylene oxide dimer, hexafluoropropylene dimer acid, and 6:2 chlorinated polyfluorinated ether sulfonic acid. Further, PFAS monitoring campaigns should include an assessment of emerging perfluorochemicals contaminated in local food and in agriculture environment to help establish more robust PFAS management guidelines. Thank you, dear Professor.